All right, welcome back to COG 376. Today we're going to talk about neural networks and language. So we've been on about all these different ways of modeling language throughout the semester. And this time we're going to get into the sort of the neural simulation version of it. So, first and foremost, neurons. You're made of them. Everything you do, say, think, see, it's all neurons firing information across themselves and at each other. You have this little outline. Dendrites catch signals from other neurons. The cell body accumulates a charge, and then it sends an action potential down the cell. Yeah, don't worry, you don't have to memorize these anatomies. Just the basics of a neuron. You've got dendrites catch the incoming information, the cell body starts to integrate the information, the axon sends it out, and then at the end of the axon is a bulb that, touches the next neuron. Cool. So, that's the basic idea. Neurons, when you're dealing with neurons, when you're looking at the way neurons work with each other, the dendrites are going to receive the input from the other cells. And once they're sufficiently stimulated, the body will send that current, the action potential, down the axon. Once that action potential causes the axon terminals to produce neurotransmitters, is what is caught by the next cell. Most importantly of this process is that it's sort of an all or nothing type thing. You can still measure quantity in terms of how rapidly a neuron is firing, but essentially it's firing or it's not, right? So that's the biology. That's the sort of the basic version of how neurons do their neuron thing. What if we wanted to do that in a fake version? Enter perceptrons. The artificial neuron, not like in medical treatment artificial, but in the sense of being a neuron that you can model in the computer. Perceptrons are essentially trying to capture, in math terms, the behavior of a neuron. So in the same way that the dendrites capture signals from other neurons nearby, the perceptron has the ability to take inputs from other perceptrons, and it's able to, it weights them together, it weights the inputs, it changes sort of let's see, how do I put this? It can adjust, each input can be weighted a different amount, right? So if we're getting inputs from one area and they're negative, but they're from another area and they're positive, that means that they will be summed together by this system of integrating the signal. So if the threshold inside the cell is passed, it will fire. Here we see, if you're used to math, we can look at it here. We have lots of inputs on the left, right? You have the eyes, different inputs, and they are different values, right? They're either on or off, some maybe even the firing rate, but the value comes in, and then it's multiplied by some weight, so it changes. It's either inverted or zeroed out or positive or whatever. And then you sum that result across that, the sigma, right? So the cell inside is saying, hey, here's a bunch of signals coming in. There's different weightings on each signal, but I'm going to sum all those up. And if that crosses the threshold T, then I will send the signal on. I will fire my own signal forward. I hope that's making sense. The math is a little kludgy, but if you've ever seen the sum sigma, I mean, that's the most complex thing here. The whole idea is we're trying to do the same kind of thing. Say, hey, neurons can respond to other nearby neurons, and that's pretty good. That's pretty useful. What is it useful for? Well, that's what we're going to get into. So this is the basic premise. This is the artificial neuron. What can we do with it? Well, to start, it's important to recognize that it can do a lot of things on its own. So our model neuron, it doesn't really look like much, but one of these neurons alone, these perceptrons alone, can do some basic operations. It can do some basic Boolean logic. It can capture and, it can capture or, and it can capture not, these operators, right? So and is, we should only respond if both inputs are present. So the sum has to be over a certain threshold, right? Or would be, I should respond if either input is present. And then not is, I should respond the opposite of what's given to me by a negative weighting. Let's look at each of these just briefly, and we'll recover what these Boolean operations are, right? So if you're not familiar or you're rusty on these things, we'll cover them in a sec. So here are some basic Boolean operations. Now, before I move into that, it should be clear that Boolean operations, they're just like truth tables, right? If this and this are present, then that should be yes, right? The whole point of that is that you're transforming bits, the most basic unit of information, on or off, and you're transforming them, you're combining them together. So the whole point is that if you can do something with bits, you can do a lot. Think about your computer, for example. So, a perceptron that is a not perceptron. Here's how it will be set up. First of all, the not function is the input is 0, the output should be 1, right? If the input is false, the output should be true. In the opposite case, if the input is true, the output should be false. How do we capture that in this perceptron world? Well, whatever the input is, we multiply it by -1, and then our threshold for outputting our own 1 is going to be close to 0. So now if an input comes in, it gets weighed, it gets inverted or not, and then so if the input coming in is 0, the threshold is just below 0, so we say, I'm going to output a 1. If the input coming in is positive, it gets inverted by the weighting on the perceptron, right? The weighting on this input turns it upside down. And now it's no longer above the threshold. You can see I'm kind of walking through the table left to right, right? It's no longer above the threshold, so the output should be 0. This amounts to a not function. Let's ramp that up a bit. Let's do an and. What's an and? So an and means that, here we'll go right here, look at the bottom right table. The and function is the only time you should be firing is if both of the other things coming in are true. Both of your inputs have to be true for an and to fire off. If I say I want pizza that has pepperoni and pineapple, I'm not going to be satisfied if they deliver me a pizza with just pineapple, right? I'm not going to be satisfied if they deliver me a pizza with just pepperoni. It has to have both, right? So that's the and function on the right. Let's look at how it's mathed out in the perceptron. We have two inputs. We need them both to be positive, so we weigh them as positive. We multiply them as positive, as normal. That's kind of a normal weighting, would be like that. And we're going to put the threshold not low, we're going to put it just so that it takes both activations summed together to make it. So what does that look like? So the inputs, when they're 0 and 0, that's nothing. There's no signal at all. We're never going to cross threshold. We're going to not output anything. If I have only one of them, when I sum them together, that's not going to meet that high threshold, right? T is 1.9. The threshold is 1.9. And we're adding together two values, and only one of them's there. So what that means is that the only way to reach the output threshold to do this AND operation is to have them both present. They both get multiplied by their weights, which are just normal, and then we sum them up to 2. 2 is greater than 1.9. Let's fire off, right? Similarly, or. Now, if I told you, hey, I'm cool with having pizza that's either ham or pineapple. I think I said pepperoni before. Who cares? It doesn't matter. People are always going to argue about pineapple on pizza anyway, and that's why I said the contentious one. So, or has it's either case, right? Hey, give me something with ham or pineapple, right? You're going to be fine with either case, right? And that's not the exclusive or that we're used to in normal human language, but it's the idea of either of them can be true, both of them are fine too. So in this case, all we've done is we took the and perceptron and we lowered the threshold a bit so that either of them being present, either input being 1, is enough to fire. So now we see in the output end there that given the two inputs, if at least one of them is 1, we're good to go. That's 3 different Boolean operations that we've been able to capture just with a single perceptron node. Now, why? Who cares, right? Who uses Boolean? What's the deal with Boolean? These 3 operators are fundamental to any information processing. This is why the hardware of a computer is filled with OR and NOT gates, like physical electronic gates that do these exact operations. Everything your computer is capable of doing, it's doing using a combination of these 3. Now, when you start to scale up these nodes, these perceptrons, you're trying to get to a place where you can do really complex stuff, right? We're starting with basic bits and bytes and combining them. In fact, sorry, not bytes. If you're a machine head, just bits, right? We're trying to combine them into something more complex. Where do we start? Well, here's an interesting page from history. We can look at the XOR controversy. This is Minsky and Papert, 1969. So the perceptron seems like it has an upper limit when we first are getting into this space of, hey, perceptrons are a thing that we can model. It's close to what a neuron does, maybe not perfect, but it's doing something neurological-ish, right? Sure, it can do these nots, ors, and ands. That's cool, but what about this other very, very simple logical operator, XOR? It can't handle XOR. What is XOR? Exclusive OR. This is where I would say I want ham or pineapple, but not both, right? And that's the trick. It's slightly too complex for the perceptron to handle it. The issue comes down to the idea that a single perceptron only really has one threshold. It's this line in the sand that you have to say, hey, should I fire, right? It only really works with linearly separable functions. So if you look at the bottom here and on the left, you can sort of get a sense of the threshold, right? I'm only going to fire if both are present. So we're looking at the inputs on the X and Y axis, right? So the first input and the second input. There is literally a line you can draw through this chart that shows when I should fire and when I shouldn't. For the OR in the middle, on the middle chart, you see we've lowered the threshold. But the problem is, where do I draw that line for exclusive OR when I just have one line to draw? There is no way to do it. Exclusive OR needs a second line. So the point being that the thought at this time was that because the perceptron was incapable of explaining XOR on its own, that this whole line of thinking was a dead end. This is not an interesting way to model neurons. It's not really going to be powerful. This seems like an issue. Well, let's see. Can we make an XOR operation in a perceptron? Remember, XOR is only one of them can be present. I'm not going to walk all the way through this, but the point is that you can. So you combine the two inputs with two different perceptrons. Those go to a third perceptron, and one of them is doing an AND, one of them is doing an OR, and there's a NOT involved there. Essentially, it's saying, do the OR, but if the AND is there, invert it and negate the OR. Kind of makes sense? So do an OR operation, right? OR operation gives us 0, 1, 1, 1, right? Running down top to bottom. 0 for when neither are present, 1, 1, and then 1 for when both are present. Then take that, combine it with an AND that has been negated, right? So if the AND has happened, so it's essentially saying A or B and not A and B. It's a lot of Boolean algebra arithmetic stuff. Point being, By scaling up a little bit, by combining 3 perceptrons, you can create this XOR operation. It's more complex, only just slightly more complex, but it is doable with multiple perceptrons. So, given that that's the case, once there was this, this point was made, the real issue emerged in the historical take on these kinds of investigations, and that is, fine, you can jam together, as many perceptrons as you want, but that's not really an explanation, now is it? Right? There is not a strong, clear, clean explanation for what's going on. Back then, and still today, obviously, but there is a preference for theories that are clean and clear, right? Where you can explain them. The complexity of the XOR circuit alone was off-putting. How do I didn't even want to explain this to you, right? Not fully, because it's a lot of numbers and they're all kind of interconnected. It's a network analysis of a thing that is kind of hard to put into just straight up normal words. So you can kind of see where they're coming from. How do I clearly explain these weights and thresholds when I'm trying to come up with a theoretical version of how these things work? Now, I'd say that there's fine points on either side here, but this damper on the research killed research on this stuff for more than a decade. It took until the 1980s for this kind of research to get going again. So, the idea, though, is that this was a powerful concept that they downplayed a little too hard when they were getting into this, because the fact is that when you combine model neurons, combine perceptrons, it's this beautiful trick that you can do in the math, but also that your brain is doing itself. This is the reason the brain is so good. You can combine all this basic information processing stuff, Boolean logic, into more complex operations, like legit normal math, right? By chaining together Boolean switches, on and off, inverted summed, ands, ors, you can do kind of any complex information operation, because what you're dealing with in these model neurons is the basic unit of information, the bit, the on or the off. And again, this is literally exactly how your computer works. This is what it's doing right now. It's moving a lot of on and offs around in very complex ways, in very complex circuits, to make this thing that you're listening to me through do what it's doing. Every little amplitude of speaker sound you're getting out of me, every bit of light that you're seeing on the screen, that's all from combining and transforming bits. So, I hope I've convinced you that bits are powerful and that this is an interesting space to be in. So now let's talk about networks, where we take one perceptron and smush them together with other perceptrons, not just XOR anymore, right? So, what are we doing with neural networks? If you string enough of these critters together, you can get a really complex network that's capable of transforming information at an incredibly granular level, right? The bits, the on and offs, right? But the key is that it's massive and it's kind of in parallel. Now, up front, it's tricky to figure out what are you going to do with this. What helps us to describe the real beauty of what these things do is they learn. They learn how to connect inputs to outputs. You give it an input, so some kind of thing that it's supposed to detect in the world or in our modeling space, right? And you also can know what the output should be so that you can then go in and update all the weights to say, hey, you were pretty far off from the input. This is called backpropagation. And this is the way you train a neural network, or one way to train a neural network. So the idea is that you're going to go and you're going to update those weights, right? We saw the weights for Boolean operations, and they are just set at a normal value. But when you have lots of weights coming into each node, you can get some more complex interactions between them. You could have one node that hinders 10 other ones, but excites a third, a 15th one over there somewhere, right? So you have nodes that can interact in ways that, again, as we discussed, they're kind of hard to describe. So, but the trust is that if you allow these systems to get feedback from the environment and update themselves, that they will start to converge on something looking like interesting pattern matching, interesting computing, right? So the idea is that you get an error signal if so input something, right? For the Boolean stuff, you could have a node that didn't know what its weight should be, right? So the input for not is 0, and the input for and the output should be 1, right? If the input was 1, the output should be 0. The whole crux of the not perceptron required that negative weighting, right? At the start, it wouldn't have any weighting at all. So what you would do is you'd feed in 0, and it would output 0, and the system would say, hey, was that good enough? And the back propagation would come in and say, no, you were off by a whole point. So then you go in and you change the values of the weights, right? You adjust the weightings so that the next time, maybe you're closer. That's the whole idea. So if you come close to the desired outcome, you only adjust very slightly or maybe not at all. If you're far off from the desired outcome, adjust a lot. And if you're really far, maybe even kind of randomly, you're searching for the right destination. The idea is that the nodes are adjusted based on their responsibility for the error signal. Sort of how far away were they, how involved were they in that particular error production. What can you do with this, though? So if you're getting good at mapping some input to some particular output, you could call that a classifier. You may have heard of machine learning and classifiers, or maybe both of them together. But the basic idea is that what you're able to get out of a network like this is this surprisingly human concept of see some stuff and then name it, right? Now that's very coarse. That's me sort of personifying these things. But the idea is that you can have one of these systems take lots of inputs and then have only one node somewhere way up the chain that responds to a particular combined set of information. So you can have that be very simple, like a binary class of should I fire or should I not, right? Like in the binary inputs, but you can get at other things, right? So if there's a series of pixels on the screen in a particular shape, what letter do I call that? I could have 26 nodes that are all considered the letter recognizers, right? I could have systems in my brain that in our artificial neural world that take a series of pixels and convert them into, oh, this node will light up when the letter I is present. Or words, right? Here's a waveform of sound, of audio coming at you, and you heard the word you just now. You were able to take you out of the waveform and something in your head held on to it. The same thing is possible in these neural networks. You take a very complex pattern of the waveform of sound that's coming in, and you can have one node that's very sensitive to the word you and not sensitive to anything else. That node is the you node, right? So, other things you can do, you can also sort of figure out other information. So, this recognize where in a part of speech a word is in a sentence, right? Or in the image world, you could say, does this photo, this image, this square of pixels contain a specific entity? Brings us to AlexNet. This is an interesting case. So this is a network that was trained with lots of different layers. You know, it scales up and up. And we'll see that in a second. To do things like identify categories. So it studied millions of photos of dogs, millions of photos of houses, food, books, etc. And the idea is that there are nodes in this network that will light up primarily only when, say, a dog is present. There's lower levels too, so there's like edges and textures and stuff. So let's look. Here is some of what this system is excited to see, right? These are the images that would most activate the systems. We see here, for example, houses, right? This shape here is the one that is most exciting for the house model. But here's the trick. Just because that's the most exciting image to that particular neuron, that particular node there at the top, that doesn't mean that other images, like actual normal images of houses, aren't going to be the ones that are also exciting, right? So if I showed an image of a house to this system, it would pick up all these different combinations of the waves at the bottom layer there, right? Those nodes light up in different amounts. Second, as we scale up, we get more kind of rigid squares and spirals and swirls and stuff. And then finally, as we keep combining these lower level features, we get to a shape that has sort of a peak at the top and maybe a hole-ish shape in the front. That's going to be a house, my dude. Compared to if I showed it a photo of a dog, that node would no longer light up very well. But the dog snoot node would start to. This is the idea. These complex features, at the very lowest level, we're just showing pixels to this neural network, but it has been trained to pick out features. So this is the primary idea. You have a way to input basic information like pixels or maybe words or letters if we're working in language. And on the output end, the word dog is still just one of these perceptrons, but you could then have a system say, oh, when that perceptron's lit up, I'll just output the word dog. That's great. So let's talk about some neural network properties. I hope this has illustrated a bit about how they work. You know, there's a little more to it, but not actually as much more as you might think. Perceptrons we've already covered pretty solidly. So if you understand one of those, you understand how these things connect to each other. And then if you just update the weights, you can get some really complex behavior. So properties of neural networks that we find interesting in this language world. First is that they are quite flexible. So they can work with degraded and incomplete inputs, even if they weren't trained on something. So say new scenarios where it's trying to capture language it's never heard before, it can do something, right? It doesn't just crash out and die. It does something. They're also really powerful. Like we said, most types of information processing can be captured here in some way or another, provided it has something, we are good at giving it patterns to match, right? Math, language, images, we've seen some images stuff. They are teachable, so not only are they trainable, you can train them pretty easily, right? Backpropagation training is straightforward. It's this huge trial and error process. It's a little slow, but it's still great. Like it's straightforward. All we got to do is give it good inputs and outputs, and it'll work itself to the bone to figure it out. And then finally, they're fast. Now, not to train them, but neural nodes all work together in parallel. You take all the inputs, you shunt them onto the next layer, shunt them onto the next layer, and then you're done. So tons of small transformations all at once in parallel, side by side. That's the whole concept. So how do we get this into Language Town? We've got this complex, interesting, sort of abstract concept of language. How do we get this into one of these systems? The cool thing here is that it turns out symbols, language is full of them, right? That's actually a great thing for classification. Saying, hey, here's a thing, here's some letters together. Let me abstract that into a word. Or, like we just saw, an image, right? Here's a photo. My dog node is going to light up. That is language, right? We've talked about this before. Tying language to the real world. That's language, dog. Great. So let's talk about the first ways that this was applied to language. Rumelhart and McClelland, they have all these different layers of classifiers, and that's the key thing here. They're each layer is a different set of classifiers pointed at the layer below it. So at the feature level, you have visual input or acoustic input from the outside world. They're down there at the bottom. Comes in, just like we did with the images, So the feature level says, hey, here comes the visual input. I'm going to look at where the curves and lines are, for example. From the features, I can now have nodes that notice those feature nodes and say, ooh, the curly part is lit up, and so is there's a big hole in the middle part. Maybe that's a 6. Okay. Or a G, depending, right? Depending on what letters they're trained to. So features can be noticed by letter classifiers or phonemes if we're working in sound, but by the same process. That's kind of the coolest thing here, is that it's the same basic idea. It doesn't matter what the information is, the thing still works. So either way, from letters and phonemes, now we can have things that say, oh, those 10 letters are in a row. I know what that word is. Great. So the way this comes together, you see sort of the bottom-up thing here again. The stimulus work, the word work comes in. There's feature detectors, whether that's sound or vision. Who cares really for this little illustration? The point is that it gets broken up into these 4 letters, which different pattern recognizers comprehend, right? And again, these aren't literally actually letters. Those are just nodes that are capable of noticing letters. The W node is capable of noticing W's, right? And further up, the word detectors say, oh, well, look at this one, for example. The word word, it's excited about 3 of those inputs, but the last one's missing. The word fork is excited about 3 of those inputs, but the first one's missing. Only the work classifier is saying, all 4 of the things I need to be lit up are here. So that's the basic idea of their model. It's this recognizer. It's this layered recognizer. Now, the cool thing they did with it, they tried to make it learn some new things from a naive place. So learning past tense. Here's the idea. English is a weird hodgepodge language. All my English second language people, you know what I'm talking about. I'm sincerely sorry for our language. It's a big old mess. We've got the most bizarre past tense, irregular exceptions out of any language on the planet, I believe. So a lot of words are normal, clean, easy. They end in ed to make them past tense. Bake, baked. Walk, walked. Dance, danced. Nice, easy, clean, But then we got all these weirdos, like it's gave, not gived. It's went, not goed. It's fought, not fighted. This is the children thing. This is the overregularization thing that kids get into. So you have this verb that comes in, and then you have this process of, well, should I just tack the letters ed on the end? By default, you do learn that. Kids learn that first. But then they have to learn all these exceptions about how this actually, no, it's not quite right, work with it a different way. So the question on Rumelhart and McClelland's mind was, can training a neural network mimic this? Like, first of all, can you actually encode this transformation process, right? Can I get a neural network that is going to convert words from present to past tense using only the neural network? But they also try to mimic the trajectory of learning seen in children. So if I use backpropagation, if I expose the network to certain examples and then tell it, no, you didn't do that right, and make it train itself, of course, is that going to get us to the same kind of learning pattern that kids have, that actual children have, right? Who have actual neurons, not just simulated ones. So here's their model. Similar to what we were seeing before, it's sort of like You get the phonological representation, right? You get that auditory input. You break it into its features, but then they actually skip all the other categorization stuff, and they're just saying, hey, there's two feature networks. We're going to go from one feature network, whatever the pattern of features are that have been noticed here, and we're going to jump straight to another feature network that should be the transformed version. So walk, the sound walk comes in. The feature network notices all sorts of things like the L and the U and the on the K, all those things. And then the immediate output is supposed to be the walked, right? Add the D on the end of it, right? So let's walk through an example. Walk, also, I'm going to include letters in this as though they were part of the process. They aren't. It stops with these little features things, but here's the idea. Walk, and the goal is that we know we want is the word walked, right? So here's how this system would break it down. Walk comes in, it gets converted into walk, right? These little features, these little auditory features. I'm converting them into letters now just so we can make it a little simpler to keep track of them. But the idea is that from this broken down state, the learned weightings here in the middle are what are going to convert the whole of the input values to the past tense version, converting it to walk ed, right? And then convert that back down. I mean, that's just letters to the features, but now we're seeing walked, walked, check mark, Dunskies. And we give a little bit of a benefit to our system. We say, hey, you did good, you worked out. That works for walked. Let's do. The output that we want is did. So let's break it into our features. Do, the letters do. The learned weightings that we might have from training on words like walked, dude, no. The fact is, that's not right. So the system would see that. We would compare against the goal output, and it would say, okay, I screwed up. I'm going to adjust my weights and change things around. So now, ultimately, when I go for do to did, we get to this step. As the conversion, it no longer preserves the oo, it has learned to override it with the id into did. We did it. Yay. The more you have to change and deviate from that system, the more likely it's going to take you extra effort. So after a lot of training, you might be able to capture something like go to went. Go. The weightings are there. Go gets overwritten entirely by went. Right? That's the idea. So they trained them, and they wanted to see what happened. Now, first, if training these models sounds like it might take an eternity of giving feedback to get it to converge on this idea of, these are very complicated numerical mishmashes going on in there. The weightings between all of them are messy. So the question is, how do you get there, right? And the answer is gradually. That's one of the drawbacks of training up neural networks is they need a lot of examples. But it takes kids a long time too, and that's what they found. Their patterns of learning in the neural network, so this is the percent of the correct features, right? The irregular words, with the features present, it takes them a long time to start adding the id to do, right? They start low. The regular features it learns pretty quickly, or the regular words it learns to add the correct ones pretty quickly, but the irregular ones lag behind. It takes longer to get more of the word correct. So the irregular words, the percentage of the correctness of those words, grew more slowly, illustrating the overregularization process. This pattern is nearly identical to human kids, which is super cool. So, Rumelhart and McClelland demonstrated how one can encode language processing in neural networks. So they weren't the only ones to do this, but that's what we've seen of them so far. They also showed how this overregularization error works in a neural network, which is cool for understanding maybe the neural networks have something going on that looks kind of like what brains do. That's cool. And they also demonstrated that these learning patterns, even the learning pattern, is a little like what humans are doing. Maybe not perfectly, but so children do learn a lot faster than these models, right? It doesn't take them 10,000 times to start to understand these words, but they have lots of other systems going on, right? They have internal practice, all this kind of cool stuff. But the pattern of when they master irregular words occurs pretty roughly in the same progression, right? Remember, we have more of the letters are replaced in went than in did than in walked. So that's all neat, huh? What the hell do I do with this information? So, where do you begin? So these neural networks are super flexible. They can compute anything, in quotes, How should I apply them to a language model? What are we doing here? They aren't almighty, first of all, but they are super flexible. So that's actually the idea that's at the heart of a neural network, is that any pattern that you want recognized or transformed in that way, you can do that. You can make that happen. You just got to be careful about how you construct the way the model can detect the inputs and submit the outputs. So as long as you can accurately define the information needed to be matched and classified and transformed, you can probably set up a neural network to do it. Language is no exception. But along those lines, we have some interesting use cases we can throw out there. Depending on what we define at each step in the various classification processes, you can capture a lot of different use cases. So, for example, summarization. The idea in summarization is match a larger description to a more succinct version. That involves reducing information, right? You say, here's a whole paragraph about this short sentence. The idea kind of scales up nicely, right? So it involves mapping the shorter summative phrases to their full paragraphs and such, right? I wish I had some examples, but I've been short on that capacity lately. So, machine translation too. So this one actually kind of makes sense. This is kind of like what we just did with the little features being converted from past tense to normal tense to past tense. Convert one language to another, right? Words from one language map quite easily onto words from another. Now, obviously, there is a lot more to translating a language than just, hey, here's one word, make it from English to Spanish. That's not really going to fly, because Spanish-speaking cultures and countries use different like cadences and different constructions of sentences and stuff. So it's not going to be a one-to-one, but even those can also be changed, right? So you may translate individual words, but then you may also translate at the level of whole sentences. Both of them have sub-features that can be captured by the different nodes in these networks. Finally, we can actually generate language. We can use the previous words to generate new ones, and then include those new ones and repeat. Very much like what we just saw previously with n-gram models, right? We can use a neural network model to predict and generate language one word at a time. Similar concept of how we used n-grams and context vectors, right? We're saying, okay, I've trained the system on lots of passages of length n. I'm going to generate a new word, and then I'm going to drop that into my inputs and keep going, right? We see this little moving window here going on. And remember the hidden layers, the output layers, all that stuff that we've sort of covered how those work. So, pros and cons. Why would you use this? Why might you not? These systems they're super slow to train. It takes hundreds or thousands of examples for each word. Adding new training data can really disrupt the training of the original stuff. Not always, but you never know with these networks. They're hard to sort of figure them out in that way. Another thing is that they're not not plausible exactly. Brains don't actually do backpropagation. There's no way for that to work. That's not how neurons are biologically set up. You can't go run backwards through the neural trace. That's just, no one's there to do that. But also, and this is the real tricky part, is that they're super difficult to explain. You may train a neural network for a year on types of information and stuff, but it's the black box problem. And that is that all the connections between the different parts of your model are math. You're not necessarily going to be able to understand it. And you won't really be able to check in on how it works. Remember when we were messing around with the Markov chains, the n-gram models? I showed you exactly how the memory worked, right? I could print it out for you. I couldn't print out the weights and connections of a neural network, or I literally could print them out, but they would be absolutely meaningless to our eyes, right? Now, that's the cons. There are issues, of course. Every method has its issues. But the pros are pretty cool too, and we already talked about some of them. First of all, once it's trained, it's super stable and reusable. If you train a model a million times, it becomes a very robust, tuned thing. Also, it doesn't really grow in size. Remember, every node is just, the information's all bound up in the differences and the weightings between nodes. It's fast if you're running things in parallel, so it's only as many layers as there are, as how many steps there are. It's flexible, so it can generalize to unseen content. And it's robust in a general sense. This complexity, you can capture a lot of nuance that can actually be hard to describe. This is actually the positive side of the black box problem. The idea that because this thing is a black box that runs on math, it can capture things that we might not have been able to explain. So, there's lots of types of neural networks out there. There's deep neural networks. There's sort of lots and lots of hidden layers, what's called deep learning. So they can get very complex with the things that they will learn. For example, they might come up with new categories for concepts that they use internally, right? They don't ever show them to us. We're not necessarily going to be sure about, when this 10th layer deep node is able to flag something, what does it mean? It won't necessarily be clear, but that's deep learning. That's the idea that you can add many, many hidden layers and get something really powerful. Recurrent neural networks, these are the kind that they will hold on to information. They can process sequential data. You can feed information into them and they will keep feeding information back into themselves. The idea of memory going on. Convolutional neural networks, these are the ones that are inspired by the visual cortex. That's sort of what we looked at before with the categorizer, right? It broke things down into very, very simple, mathematically sort of these vectorized, rasterized little features, right? There's also generative adversarial networks, and these ones, this is what I'm going to leave you with. This is a really interesting case. So these are powerful neural networks. They are called generative adversarial networks, and it's a trick for neural networks to just run off into the wild and improve themselves without people giving them tasks to do. That sounds a little scary, but the point is that you can set up two networks next to each other, and they're going to do this sort of back and forth, trying to trick each other. So there's a forgery artist and a detective, and they're both trying to outsmart each other. So the generator is the forgery artist. It's going to try and create an image. The discriminator is going to attempt to identify it. The generator gets rewarded for fooling the discriminator, and the discriminator gets rewarded for spotting fakes. So the generator is moving further and further into a space where, hey, I make very real images. The discriminator is moving into a space of, hey, I'm good at spotting fake images. They fight, they butt heads against each other over and over, and then we get images like these. But, look, at first glance, this is actually kind of impressive. These were generated images. But at second glance, things don't look so great all the time. How come there's so many eyeballs on that mushroom? That coffee cup doesn't look very stable. In fact, it looks a little bit kind of bulbous down there. This dog's legs are not great to look at. That rocket ship is chapstick? Lipstick? So they're almost convincing. Looks like this detective network need a little more energy put into it. But the point is that the longer they run, the more they can butt up against each other, using the power of each other's neural systems to help spur them forward. It's very cool. And leaves you with this question: which one of these faces was generated? These are pretty high power. The freaky truth is that neither of these people exist. You can kind of tell, you look at her teeth. It's like, ugh, that canine goes a little too far down. But that's the idea. So neural networks are super powerful. As long as you know what's going into them and out of them, you can set them up to learn patterns. So, in summary, neural networks capture something fundamental to how our brains actually work. They aren't perfect, but their ability to combine extremely granular information processes into more complex ones makes them incredibly flexible. This is also what your brain does. Because of their flexibility, they let us do a lot of interesting stuff with language. We just got to be sure we're defining the inputs and outputs well. And that's it. That's the concept for you. As always, final thought. Consider the XOR controversy, that models should focus on staying clean, obvious, and explainable. Now consider how machine learning algorithms impact our information environment every day. Recommenders, feed selectors, that kind of stuff. Do you think they were right to err on the side of caution? Or did we miss a full decade of important development of these algorithms? All right. That's it. Thanks. Take care.